Welcome back to the deep dive. Today we're getting into the real guts of it. We're talking about how to build a masonry wall that's going to stand for 100 years, not just until the warranty runs out.
That's right. We're going from the footing all the way up.
Yeah.
The whole idea is to connect the craft, laying a perfect course with the rule book, the stuff the inspector's going to have circled in red pen.
Absolutely. It's about the physics of it all. How the load gets to the ground, how we fight water, and what happens when the earth itself decides to push back.
It all comes down to understanding the why, not just what the code says, but why it says it. So we're going to start right where every job starts, at the bottom, the foundation.
Okay, let's do it. When you're looking at a set of plans, the first question you got to ask yourself is, what is this foundation wall actually doing?
Is it holding up the roof, or is it just there to keep the dirt out? Load-bearing or non-load-bearing? That one decision changes everything.
Yeah, I tell the apprentices, look for the beam pockets. If there's a big steel I-beam sitting on top of that block wall, you know it's carrying weight. Serious weight.
And that's not just the weight of the structure itself, the dead load. It's also the live loads, people, furniture, and the big one up here, snow. All of that has come down that wall.
So you've got to follow those structural drawings to the letter. No substitutions, no, we'll make it work.
And that's where we hit our first big warning from the code. Most of the simple rules, the ones in Part 9 that we all use for houses and small buildings, they're based on one huge assumption.
Ah, here we go. You're talking about drained earth, right?
Well,
The perfect world scenario.
exactly. The code's happy little fantasy land where the soil is perfectly drained and only pushes against the wall with the force of a fluid that weighs about 480 kilos per cubic meter.
Which is, almost never the case on a real job site. You've
Yeah.
hit clay, you've got a high water table, you get a spring thaw.
And suddenly that assumption is out the window. If you expect any kind of extra pressure, what the code calls surcharges, you're in a different ballgame.
Surcharges being what? A driveway right next to the wall? Heavy equipment?
Or just water. Saturated soil, that's the biggest one. The moment that soil gets soaked, it stops acting like 480 kilos and starts acting like a fluid closer to 1,000 kilos per cubic meter. It's double the pressure.
And a standard Part 9 wall isn't built for that.
Not even close. If you know your building is a swampy area, you have to kick it up to a Part 4 engineered design. If you don't, you're looking at a bowed wall. A failure.
You see those horizontal cracks right in the middle of the wall. That's the sign, isn't it?
That's the bending moment maxing out. The wall is literally being snapped in half by water pressure. So, rule 1, know your site. If there's any doubt about water, you need an engineer.
Okay, so assuming we're on a good site, we're pouring the footing, you can't just use a standard footing width for a multi-story masonry building.
No, and it's a detail that can get missed. For an interior load-bearing masonry wall, the code is very specific. You have to add 100 millimeters to the minimum footing width for every single story of masonry that's sitting on it.
So a 2-story block wall needs another 200 mils of footing width to spread that load out.
Precisely. It's a cascade. The weight of the top floor adds to the floor below it, and all of that concentrates right at the bottom. The footing has to be able to handle it.
All right, footing's poured, we're ready to lay block. You grab a block off the pallet. But they're not all created equal, are they?
Not at all. And this is a huge compliance point. First off, they all have to meet the CSA standard. But the number you really need to care about is the compressive strength, the MPR rating.
Megapascals. And there's a big difference between a 10 and a 15.
A massive difference. And it all comes down to where that block is going to live. If that block is exposed to weather rain, snow, ice, it has to be at least 15 MPa.
And if it's protected, like the inside part of a cavity wall.
You can go down to 10 MPa. The reason for the difference is water. A 15 MPa block is denser, less porous, it won't suck up as much water.
So if you use a 10 MPI block on the outside, what happens when it freezes?
It fails. The water inside it expands and the block just disintegrates. It spalls, it cracks. We call it freeze-thaw degradation. It's a durability issue, and it will destroy the wall over time.
I've seen guys try to get away with it by saying they'll parge the wall.
That parge coat isn't going to last 100 years. The block itself has to be rated for the exposure. And that brings up another specific warning from the source material.
The cellular blocks.
Yes, the lightweight, solid, load-bearing cellular blocks. You are absolutely not permitted to use them where they're exposed to weather, period.
They just can't handle the moisture.
They can't. If you use them in a protected interior spot, they still need to have a minimum strength of 5 MPa, but never, ever on the outside. You have to check the specs on the delivery slip against the drawings. No exceptions.
Got it. 15 outside, 10 inside. Now let's talk about what holds it all together. The The mortar.
The glue. And just like the block, the type of mortar you use is critical, especially when you go below grade.
This is a big one. I see a lot of confusion about this on site.
It's probably the most common foundation failure I see flagged by inspectors. For a reinforced block foundation wall, the mortar must be type S.
Not type N, which is what we use for most brick veneer above grade. Why type S specifically?
It's all about flexural strength, bending strength. Type S has more Portland cement in the mix, which makes it stronger not just in compression, but in resisting those sideways forces from the soil pushing in.
Ah, so it works with the rebar.
It works with the rebar. The whole point of reinforcing the wall is to handle that lateral load. If you use a weaker, softer mortar like Type N, the blocks can't transfer the load to the steel effectively. The wall will crack and fail under pressure much, much sooner.
So using type N below grade is basically kneecapping the whole structure before you even get out of the ground.
It's a guaranteed failure, a fundamental code violation.
All right, foundation's done. We're above grade. Now we're into the part everyone sees, the brickwork, the building envelope. I always tell people the brick wall is like a raincoat, but it's a raincoat with holes in it.
That is the perfect analogy. The single biggest mistake people make is thinking that a brick wall is waterproof. It is not.
Not even close. Every brick is a sponge. Every mortar joint can let water in, especially with a bit of wind pressure behind it.
Exactly. The outer wife, the brick you see, its job is to be the first line of defense. It sheds the bulk of the water. But you have to assume that water will get behind it.
And the whole system is designed around that fact. That's why the space behind the brick, the cavity, is the most important part of the wall.
It is the hero of the entire assembly. That air gap is what stops the moisture from getting to your interior structure. It's what the code calls a capillary break.
So let's talk size. What's the absolute bare minimum for that airspace?
The code says for a capillary break to exist, you need a drained and vented airspace of not less than 9.5 millimeters, about 3/8 of an inch.
But that's just to stop water from, like, crawling across the gap, right?
That's just for capillary action. For managing bulk water, real driving rain, you need more. A lot of people see that 9.5 mil number and stop there, but that's a mistake.
So what's the real number we should be shooting for?
For a standard masonry veneer wall, the cavity needs to be 25 millimeters, a full inch. And for a true cavity wall, it's even better at 50 millimeters, or 2 inches.
And that extra space isn't just for water, is it? It's for something else. It's for us. It's for our mistakes.
It's tolerance. It's for the mortar droppings, the snivels.
Oh, snivels! The absolute enemy of a good wall. You get one careless guy on the crew, and by the end of the day, you've got a 4-inch pile of mortar at the bottom of the cavity.
And that pile of mortar completely destroys the system. It acts like a bridge for water to get from the wet brick straight across to your backing wall. Or worse.
It builds a dam.
It builds a dam. It blocks the weep holes, traps the water, and soaks the bottom of your interior wall. You end up with a rotten sill plate, mold, everything.
So what's the fix? How do we stop it? It's all about workmanship, isn't it?
It's 100% workmanship. It's
Yeah.
about proper bedding of the mortar so it doesn't squish out like crazy. But on a big job, the best way is to use some kind of physical catch.
Like a piece of wood or a screen you drop down in the cavity.
Exactly. Drop a board down there, and at the end of the day or at the end of your lift, you pull it up. If it comes out clean, you know your cavity's clean.
That's a great tip. And it's so critical because of what comes next. The flashing.
Right. The code says your flashing has to be installed underneath your weep holes. Well, if the base of your cavity is full of snivels, the water can't even get to the flashing. The whole drainage plane is compromised before you even start. A clean cavity is non-negotiable.
Okay, so we've got a clean 1-inch cavity. Now we need to get the water out and let the air in, flashing weeps and vents. Where does the code say we absolutely have to have flashing?
It's non-negotiable in a few key spots.
Yeah.
Under any jointed masonry windowsill, for sure. Over the top of any window or door opening if it's not well protected by a deep roof overhang.
Right. If the eave is small or the window is low, you need that head flashing.
You do. But the most critical one for our cavity wall is the base flashing, the one that sits right at the bottom, just above the foundation. The installation here is everything.
This is where you can create a disaster if you don't know what you're doing. There are 3 rules for this, right?
3 non-negotiable rules. First, that flashing has to be embedded at least 25 millimeters, 1 full inch, into the inside withe, into the backing wall.
Not just stuck to the face of the sheathing paper, you've got to go into the block or the backup studs. Why is that so important?
Because if any water gets behind your air barrier membrane, it's going to run down the face of that backing wall. If the flashing is embedded, it catches that water and directs it out. If it's not, the water runs right past it and into your sill boat.
Okay, that's number one. What's number two?
Number two, the flashing has to stick out at least 5 millimeters past the face of the brick below it. It needs a drip edge.
Just little lip, so the water drips clear instead of curling back under the wall by surface tension.
Precisely. And number three is the one that really matters for getting water out. The flashing has to have a slope, a positive slope toward the outside.
So gravity does the work for you. Even a tiny slope makes a huge difference. If it's dead flat or worse, slopes back.
You've just built a gutter that directs water into the building. It'll pool on the flashing, sit there, and rot everything it touches. It has to slope out.
Okay, flashing is in. Now we need the exits. The weepholes. This is where site tradition and the code really seem to butt heads.
Oh, this is a big one. The old rule of thumb everyone was taught was a weephole every 3 bricks.
Yeah, you stuff a piece of rope in the joint, pull it out the next day, done.
The problem is that's often a code violation now. The rule is that weepholes can be spaced no more than 800 millimeters apart, center to center.
Okay, so let's do the math. If you're using a standard modular brick that's, say, 240 mils long, 3 of them is 720, you're good.
You're good.
Bad.
But what if you're using a longer, more modern brick? A 300 mil brick. 3 of those is 900 millimeters. You're over the limit. You're in violation.
So with that brick, you'd have to put a weep hole every second brick to stay under 800.
You would. And an inspector with a tape measure will catch that every single time. The 800 mil rule is there for a reason. It's to guarantee enough drainage capacity no matter what size brick you're using. You have to do the math for your unit.
Whether you're using a rope or those little plastic inserts, the spacing is the key.
It is. And remember, the weeps at the bottom aren't just for water out. They're also for air in. You need vents at the top of the wall, too.
Right, under the soffit, usually. You leave an open head joint.
And what that does is create a chimney effect. Air comes in the bottom, weeps, flows up through the nice clean cavity, and exits at the top. It's constantly ventilating the space and drying out any residual moisture. It's a complete system.
Okay, so we have a wall that can handle a load and a wall that can handle the rain. Now we have to protect it from the moisture we create on the inside. Air and vapor barriers.
And this is where a lot of confusion comes in, because they sound similar, but they do 2 completely different jobs.
So break it down for us. Air barrier versus vapor barrier.
An air barrier stops airflow. Bulk air leakage. Think of a gale force wind of moist air being pushed through a tiny crack. A vapor barrier stops vapor diffusion. That's the slow microscopic movement of individual water molecules right through a solid material.
I like to think of it as a flood versus a mist. The air barrier is there to stop the flood.
That's a perfect way to put it. And because it's stopping a flood, the single most important word for an air barrier system is continuity.
It has to be a perfect sealed envelope.
Absolutely. Every joint has to be taped or sealed. And it has to be sealed around every single penetration. Every pipe, every wire, every electrical box. A tiny hole around an outlet box can pump gallons of moisture into your wall over a winter.
The peel and stick membranes are great for this, but you have to be meticulous with the details, the taping, the sealing.
It's all in the details. Now, the vapor barrier, the thing that stops the mist, that's different. For the vapor barrier, the most important thing is placement.
It's all about where it is in the wall assembly, the warm side rule.
The warm and winter side rule, to be precise. The code says any material with a low vapor permanence, think 6 mil poly, foil-faced insulation, some rigid foams, has to be on the warm side of the insulation.
Okay, so on the inside face of the studs in a cold climate, why? What are we trying to prevent?
We're trying to keep the surface of that vapor barrier warm, warm enough that it never gets cold enough for condensation to form on it. It's the same reason your bathroom mirror fogs up. Warm, moist air hits a cold surface.
The dew point.
The dew point. You want your vapor barrier to always be warmer than the dew point of the air inside the house.
So what happens if you put it in the wrong place? Let's say you put a low-perm rigid foam on the outside of your studs on the cold side of the wall.
You've just created a condensing surface right inside your wall. Warm, moist air from inside the house will slowly move through the drywall and the insulation. It will hit the back of that cold foam sheathing, and it will turn into liquid water.
And because the foam is a vapor barrier, the water is trapped.
It's trapped. It soaks your studs, your sheathing. It's a recipe for hidden rot and mold. The wall gets wet from the inside out. It's a catastrophic failure.
Which brings us to thermal bridges. You can have a perfect air and vapor barrier, but if you have a cold spot, you're still going to have problems.
A huge problem. A thermal bridge is just a pathway for heat to get out. A steel stud, a concrete slab edge. And where the heat gets out, the cold gets in. That creates a cold spot on your interior wall where You guessed it.
Condensation forms. You see the mold growing in the corner of the room.
Exactly. And the code is really specific about how to deal with this, especially where, say, an interior partition wall meets an exterior wall. You have to prevent that cold from traveling down the partition.
So how do you do that?
You have to insulate the penetrating element. The rule says you have to extend insulation along both sides of that interior wall for a distance equal to 4 times its uninsulated thickness.
Wow. So for a standard 100 mil block partition wall, that's 400 mils of insulation running back into the room on both sides.
That's the requirement. It's about dissipating that cold spot, so the surface temperature of the drywall never drops below the dew point. It's a detail that gets missed all the time, but it's critical for preventing long-term moisture issues.
Okay, let's go back outside, back down to the ground. Let's talk about when the earth fights back. Retaining walls.
And foundation walls in bad soil. This is where we come full circle back to hydrostatic pressure.
That's the big one, the wall killer.
It is. Remember, the basic code assumes soil pressure is like a 480-kilo fluid. But when that soil is saturated with water, the pressure more than doubles. And no standard unengineered wall can handle that force.
It will bow, it will crack, it will fail.
So if you know you're dealing with hydrostatic pressure, the problem isn't the wall, it's the water. The only solution is drainage.
Get the water away from the wall before it can build up that pressure.
100%. The code makes foundation drainage mandatory. You have to have a drain pipe or tile at the bottom of the footing, and it has to be covered by at least 150 millimeters, 6 inches of clean gravel or crushed rock.
That gravel layer is key. It lets the water get to the pipe without clogging it with silt.
It does. And you also have to damp-proof the wall itself to stop moisture from just wicking through the block. And if you know you have real water pressure, you have to upgrade from damp-proofing to full waterproofing.
Now, let's take that same idea and apply it to a freestanding retaining wall holding back a hill. Why are the weep holes in that wall so important?
It's the exact same physics. A retaining wall is designed to hold back soil, not a swimming pool. If you don't give the water a way out, the area behind the wall fills up like a bathtub.
And that hydrostatic pressure builds and builds until something gives.
And it's always the wall that gives. It'll tilt, it'll crack, usually after a big rainstorm or during the spring fall when all that frozen groundwater melts at once.
So those weep holes are basically pressure release valves.
They are the single most important feature of a successful retaining wall. They let the pressure bleed off. That water has to be directed somewhere safe, to a ditch, a sewer, a dry well, but it has to get out from behind the wall. Without them, failure isn't a possibility, it's an inevitability.
Wow. We have really gone from top to bottom on this. When you lay it all out, it's clear that building a wall that lasts a century isn't about one big thing. It's about 1,000 tiny details done right.
It really is. It comes down to managing loads and eliminating water. If I had to give a final checklist for compliance, it would be this. First, check your block strength. 15 MPa for anything that sees weather. No excuses.
And use type S mortar below grade if there's rebar in the wall.
Always. Second, your weep holes. The maximum spacing is 800 millimeters. Measure it against the brick you're actually using. Don't just guess every 3.
And from my side, the workmanship side, keep that cavity clean. No snivels. It's the engine of your drainage system. And make sure that base flashing has a real positive slope to the outside.
And finally, get your barriers right. The vapor barrier goes on the warm side, period. If you put a low-per material on the cold side of the wall, you're building a rot factory.
It's those little things that separate a pro from someone who's just slinging mud. It's the difference between a legacy project and a lifetime of callbacks.
Right, and we've talked a lot about water and soil pressure, which are physical forces, but I'll leave you with one final thought, something a little different. The code also warns about a chemical problem you can run into with soil. Pyrite expansion.
I've heard of that. It's a mineral in some types of rock.
It's an iron disulfide, usually found in shale. When it gets exposed to air and water, it oxidizes, and it can expand with incredible force.
Yeah.
It can literally heave a concrete slab or a foundation right out of the ground. It's not pushing sideways, it's growing from underneath.
So it's a totally different failure mechanism.
Completely different. So my question for you, for everyone listening, is this. Knowing that all the standard rules assume predictable, drained earth, what do you do if you're on a site and you see that weird flaky shale? If you suspect a chemical issue, not just a physical one, what's your next step to protect that footing when you know the rule book doesn't cover it? That's the kind of problem solving that goes beyond just following the code.